G'day. Today I want to discuss prime numbers. Now the prime numbers are part of the natural numbers, which you'll remember have the symbol n and are just 1, 2, 3, 4, 5, 6, 7 and so on. The prime numbers are given the letter P. What is a prime number? I want to go over to the whiteboard and show you. Natural numbers are either prime or composite. If I have, say, the number 6, and I want to divide it into smaller groups of the same size. Now I can do that by, I have 2 3s. Okay. 3 2s. Numbers like this are called composite. So I can safely put 6 here. But let me look at the number 5. Again, I want to put this number into smaller groups of the same size. But when I put 3 and 2, that's not correct. They're different. Or if I divide it like this, that's not correct. So with this number, I cannot put it into smaller groups of the same size. And such numbers as this are called prime. So 5 goes here. Let's have a look at 4. 4 I can turn into 2 groups of even size. 4 is composite. Now 3 I can divide like this. But they're not the same size. So 3 is prime. Of course, I can make this into 3 groups of 1 or 1 group of 3. But I can do that with every natural number. But that's the thing about a prime number. That's the only way you can divide a prime number. You can divide it in ones or you can divide it by itself. And what you divide by is called a factor. So a prime number has only 2 factors. Itself and 1. So, to return to the worksheet, we have a definition. A prime number is a natural number with exactly 2 factors, itself and 1. Question 2. Can you write down the first 6 prime numbers? Well, the first one to consider is 1. But 1 does not fit our definition. 1 has only 1 factor, 1. And a prime number needs 2 factors. So 1 is not prime, but 2 is prime, and 3 is prime. 4 is composite. 5 is prime. 7 is prime. Notice all the even numbers are now, from now on, are composite. 2 is the only even prime. 9, though, is also composite. It's 3 squared. 11 is prime. And 13 is prime. And there are our first 6 prime numbers. So we want to find the primes up to 100. An ancient Greek mathematician, Eratosthenes, devised a very easy way to do this, and he used a grid. We know the first 4 prime numbers, so let's circle those. That's 2, 3, 5, and 7. Now I'm going to go through the rest of this grid and cross out the multiples of those numbers. And each of those numbers, of course, will not be prime, being a multiple of another number. So first of all, as I explained already, 1 is not prime. The multiples of 2 start with 4, 6, 8, 92, 94, 96, 98, 100. Now, 3. But you'll find that some of these have already been crossed out. 93, 99. Now I can go through and cross out the multiples of 5. Well, that's very easy. They've already been crossed out because they're multiples of 2. And lastly, the multiples of 7. 49, 77, 91. The next question is, do I need to check for 11? Because that's my next prime, isn't it? Well, we have two numbers, the product of which is less than 100. So if one of those numbers is greater than 10, for instance 11, the other one will be less than 10. And we've already checked for them. The answer here is no. So now I can go through the grid and circle all the prime numbers. 11, 13. So in question 6, I ask you to list the prime numbers up to 100. So you should be able to do that using your grid. In question 7, I ask you how many prime numbers there are up to 100. So it's just a matter of counting them. 1, 2, 3, 4, 5, 6, 24, 25. There are 25 primes up to 100. Now there's another question here that asks you about twin primes. I'd like you to find the twin primes in the grid. Well, twin primes are separated by just one even number. So here we have 3 and 5 separated by 4. That's a twin prime. And 5 and 7 separated by 6. So the twin primes here are 3 and 5, 5 and 7, 11 and 13, 17 and 19, 29 and 31, 41 and 43, 59 and 61, 71 and 73. Okay, that completes page 1 of the worksheet, and I'd like to go over to page 2. Mathematicians have always been fascinated by the spread of the primes, whether there's some pattern that makes it easy for us to find them. So let's have a look at some of the patterns in the prime numbers. I want to look at their occurrence within limits. So here, the limit is 1 to 100, and on page 1 of the worksheet, we found that there were 25 in the first 100. Well, that's 25%. Now here are the numbers between 101 and 200, and if we count them up, we find there's 21. In the next 100, there's 16. And the 100 after that, 16 again. There's 17 between 401 and 500. Only 14 in the next 100. 16, 14, 15, and 14. So here is a drop, but it's only dropping slowly. But as the numbers get larger, this thinning out becomes more obvious. Between 1 and 1,000 there are 16.8% overall. Between 1 and 10,000 there's only 12.29%. And between 1 and 100,000 only 9.59%. And between 1 and 1 million, 7.85. So the answer is they are thinning out. The primes are thinning out as the numbers get larger. Question 10 asks you, how many twin primes are there between 1 and 1,000? Well, on this chart here, I've marked all the twin primes, highlighted them. There are 27 there, and there were 8 between 1 and 100, you remember? So that is 27 plus 8, there are 35. There's really quite a number of them. Question 11, what is the largest prime gap? Now a prime gap is a gap between one prime number and the next. In this table, the largest prime gap is here, between 887 and 907. There are 19 composite numbers. And question 12, are the prime numbers an infinite set? Well, this question was answered over 2,000 years ago by this man, Euclid, using a very neat proof. And I'll explain it to you on the whiteboard. Euclid proves the primes are infinite by disproving that they are finite. He does this by assuming that he knows all the prime numbers. So say they were A and B and C. So he takes the product of those primes and then he adds 1. So let's call this new number Q. This number Q is not divisible by any of the primes listed. So what sort of number is Q? Well, it could be a new prime, that's possible. Or it could have new prime factors that are not in the list. So, if it's a new prime, you can incorporate it into your list of known primes. And if they're new prime factors, you can incorporate them into your list and then repeat the process. And you can repeat it endlessly. So therefore, the primes are infinite. Now let's have a few examples. Say you thought the primes were 2, 3, and 5, and then you add 1. Well, that's 30 plus 1 is 31, and that is prime. Say you thought they were 2, 3, 5, and 7. Well, that would be 211, and that also is prime. If I multiply 2 by 3 by 5 by 7 by 11 by 13 plus 1, I get 30,031. And that is not prime. It equals 59 by 509. So in this case, we get 2 new prime factors to add to our list. Interestingly, this also often happens when we subtract 1. So we have here 2 by 3 by 5 is 30 minus 1 is 29. Now you remember when we added 1 we got 31, and we've ended up with a twin prime, 29 and 31. We could try that again. 2 by 3 by 5 by 7 minus 1, well it's 210 minus 1 is 209. Is 209 prime? No, it's not. It's 11 by 19. Euclid's proof of the infinity of the primes is regarded as one of the best in mathematics. For question 12, are the prime numbers an infinite set? Well, we see yes, they are. Now the rest of this worksheet, I want to look at a particular type of prime number known as a Mersenne prime. They're named after this French mathematician. And what he did was he took 2 to a power and then subtracted 1. But the power is itself prime. I give an example here. 2 to the second power, well that's prime. Minus 1 is 4 minus 1, 3. Is it prime? Yes, it is. 2 cubed minus 1. Well, that's 8 minus 1, isn't it? Which is 7. Is it prime? Yes. Two to the fifth power minus 1 is 32 minus 1 is 31. Is that prime? Yes. 2 to the 7th power is 128 minus 1 is 127. Prime? Yes. 2 to the 11th power minus 1 is 2047. Is that prime? No. That number is 23 times 89. 2 to the 13th power minus 1. Is it prime? Yes. And 2 to the 17th power is 131,071. Is it prime? Yes. Now this is the largest prime number found to date. It was found by Curtis Cooper of GIMPS. They also found the 48th Mersenne Prime. This is the 49th. But I wonder if you can appreciate how big this number is. Many people know a googol, which is 1 followed by 100 zeros. Well, this number is much, much larger than that. This number has millions of digits. If you're interested in this, why don't you look up GIMPS and Professor Curtis Cooper on the internet.